Hi friends, my name is Vishal Ganore. I am final year NPTEL student from IIT Guwahati, Mechanical Department. So today we are going to see the experiment on venturimeter. As you know, venturimeter is the device used to measure the discharge through pipe. So we are going to see the basic geometry of venturimeter. As the venturimeter is very important applications of Bernoulli's equation. So if you look at the basic configuration of venturimeter, you will see this kind of arrangement in which there are series of sections. I will explain this one by one. These sections you can see is section number 1. This is the inlet section. The fluid, any kind of fluid will enter from this side to the inlet section, and then this is second section. This is called as a convergent section. And this convergent section is followed by this simple small straight line section. This section we are calling it as a throat, and then this throat section is again continued by a divergent section, and this divergent section is followed by this another section, that is we are calling it as an outlet section, from which the fluid can flow out from the venturimeter to the outside. So if we look at the convergent and divergent section, the slope of convergent section is more than divergent section. Maybe this angle is varied from 18 to 20 degree, and for divergent section this angle is varied from let's say 6 to 7 degree. In venturimeter there are two piezometers are mounted here. One for inlet section and other for throat section. So this is the height of water fluid column inside first piezometer, and this is the second. H2 is the height of water column or any fluid column in throat section. Friends, I will explain one by one the basic apparatus of venturimeter. The basic cycle starts from the pump. Pump is mounted here. Now flow for flowing fluid we are taking at water. So it is a water pump. So from pump will serve the water from the sump, and it will water will come here inside the venturimeter. So here we can see the basic configuration of venturimeter. As I explained earlier, this is the inlet section, and water from inlet section comes into the convergent section. So water velocity will going to be increased, so that the pressure will going to be decreased in convergent section. Again, this is the throat section in which the water will enter, so that pressure and velocity will be constant as of this convergent section. And then again the water will go to the divergent section, in which the velocity of water is decreases and pressure increases inside the convergent section. Again, this is the outlet section. From here water can go out the venturi. So here we can see the different manometers are mounted. These manometers are meant for measuring the pressure at each section of venturimeter. When the water is coming inside the venturimeter, due to the pressure gained by the water, the high water, the water column will rise here, and here the different scalings are given. So we can record the height of water column, so that we can convert it into the pressure, and that pressure we are using it for calculation of our discharge. So this is the manometer, and this manometer, all manometers are connected to the common manifold here. So, and this is the pin of manifold. This is just mean for removing any kind of water. Air bubble is trapped inside the water, so we can just place this pin so that the water can be removed from here. So this venturimeter, again we have to control the flow of water through venturimeter. So this knob is there. By using this knob we can control the flow of water through venturimeter. So after controlling the flow of water, the water will come from this knob through this knob to the sump. So here this is the sump where we can store any kind of, here we can store the water. So this sum section actually basically mean for measuring the discharge of water. So here we can show, we can see here that different scalings are there, in which by using this scaling we are going to measure the actual discharge through venturimeter. Here different volumes are given, and when this is the knob, when I press this knob, the water column will rise from some, and this water column we can see here. So by taking the stopwatch we can record the amount of time required for filling particular volume of water. So that volume divided by time, we are just calculating the actual discharge through this. Then this is another flow control valve, and this control valve function as same as this control valve, but just this is controlling the flow through pump. So we are less using this, we are just using this. So just for initial recording, just we are going to use this. And this one is just press button. By pressing this we can start the pump and experiment. So this is the theoretical formula by using which we are getting the Q theoretical. But actually this is Q theoretical. This volume of discharge of water we are not getting actually. So we are introducing the new term, that is nothing but coefficient of discharge, CD. CD is equal to ratio of Q actual discharge that we are going to get divided by Q theoretical discharge. So here, this is our aim of the experiment, to find out the value of CD, and this value of CD is fixed for each of the venturimeter. So this is CD is defined as ratio of Q actual discharge divided by Q theoretical discharge. So Q actual discharge we are getting directly through experiment, as I told earlier that there is scale is mounted by measuring particular amount of volume, time required. Sorry. So our aim of the experiment is to find out the value of CD, that is we are defining as a coefficient of discharge. So coefficient of discharge CD is defined as ratio of Q actual discharge divided by Q theoretical discharge. So here first term Q theoretical. Q theoretical discharge we are just calculated using this particular formula. In this particular formula, this is A2. A2 is equal to the cross section area at section number 2, that is third section. G is 9.81, that is acceleration due to gravity. H1 is the height of water column inside this first manometer, that is H1. And this H2 is nothing but height of water column inside second manometer, that is H2. Then again A2 is over A1. A1 is cross sectional area at inlet section, that is section number 1. So using this formula we can get it as get the theoretical discharge. Now again we have to calculate Q actual discharge, so that we can calculate the value of CD. So Q actual we are finding by just some trial and error method, as some readings are scale is mounted there. So we are measuring the particular amount of time required for filling the particular amount of volume, so that the Q actual is equal to that particular amount of volume divided by time required to fill that volume. So that volume divided by time is nothing but Q actual discharge. So we know Q actual discharge, we know Q theoretical discharge. So if we divide these two of these, then we will get the coefficient of discharge, that is CD. The value of CD will ranges from something 0.96 to 0.98. Start this switch, and then this switch, so that the pump can start. Then water from pump will come to this section to the venturimeter. Through venturimeter. This is the inlet section, then convergent section. Inside this, velocity will increase so that the pressure will decrease. Then throat section where velocity and pressure remain constant. Then divergent section where velocity will going to be decreased and pressure will increase. So pressure variation along the length of venturimeter can be recorded by seeing the height of water column through these manometers. So here we can see the height of water column, this section, and again this down section, this section. So in second part of the experiment, we have to plot pressure distribution of venturimeter along the length of venturimeter. So here we can see the pressure. First of all, it highest at first of manifold, then again slowly start decreasing up to throat section, and then again it will going to rise up to outlet section. After that, the water will flow out from this particular section. So plotting of pressure distribution can be done by using this formula. We have this formula Hn minus H1 divided by U2 square by 2G. To record H1, you have to calculate height of water column at each section, that is A, B, C, D, E, F, G, H, everything you have to calculate it. That is section number 1, that is A, B, C, D, E, F, G, H. So you record each height of water column at each section. So that is Hn. So you know Hn, you know H1, that is height of water column at section number 1. So you will get this difference Hn minus H1. Then in this formula U2 is unknown. U2 is nothing but velocity at cross section area, cross section 2, that is throat section, that is velocity at section number D. So how to calculate this velocity? As you know the continuity equation, that is discharge is equal to area into velocity. So as discharge can be calculated from there, that is the actual value of discharge, and you know cross section area at throat section 2. So that discharge divided by cross section area, you will get the velocity at throat section 2, that is U2. So you will get this factor, that is Hn minus H1 divided by U2 square by 2G. So just plot this factor of, that is non-dimensional pressure drop versus length of venturimeter, then you will get an pressure distribution.